Welcome, ladies and gentlemen, to our lecture on force problems and springs. And what I'd like to do today is tell you a little bit about springs, just introduce them as a concept, and then we'll move on and we'll do some practice problems where we solve some force problems. So let's start by talking a little bit about springs. A spring is an object that can be deformed by some small amount and recover back to its original shape. Okay? So we normally think of springs as these wound metal coils like this guy right here. But lots of things can act as springs, and we can model the behavior of a lot of different things by modeling them as springs. So when we deform a spring, when we say compress it by some amount, or when we stretch it by some amount, we place a strain on the molecular bonds of the material, okay? And the bonds have a restorative force. They're trying to push back to the way that they were, and they try to restore everything back to where it was. And the net effect of this is that the spring pushes or pulls back to this point that it's sitting at when there's no net force on it. So anytime we deform a spring in some way, it always tries to push back so that it's sitting, just like this one is here, at a point where there's no net forces on it. So when we think about this one, when we compress it like this, we know that this spring will push back this way. It'll create a force that goes back this way and try to get back to this kind of relaxation point, okay? This point with no forces on it. And when we stretch it like this, we know that the spring will push back like this, okay? It'll try to pull back to its original length, okay? This effect here, when we compress it, it pushes back. This is the main effect that we get from car suspension, right? When the car goes over a big bump, the spring gets pressed in, and then it pushes the wheels back to where they were before, okay? And this one, where we stretch the spring out and it pulls back, well, this one, I always think of a trampoline, right? A trampoline, we have a big, usually nylon surface, and all around the edges there's springs, and when you jump on it, you stretch the spring, and it creates this force that tries to return it to its set point, okay? And this set point, this point where it has no net force on it, this is called its equilibrium point, okay? So this is equilibrium for the spring. And an equilibrium point is a point at which there is no net force, okay? It's the point that the spring will just sit until something comes along and interacts with the spring and forces it to do something different, okay? In general, we would say that something is in equilibrium when it has no net forces on it, okay? So anything can be in equilibrium. You can be in equilibrium sitting in your chair where gravity is pulling down and the normal force is pushing up, but barring something coming along and interacting with you, you're just going to stay sitting in the chair, okay? You're not going to suddenly be moved. There's no net force on you, okay? So this is tied very closely to Newton's first law. Remember that things will keep their velocity unless there's a net force acting on them, okay? And this equilibrium point, it can be with some quantity for velocity. It can be with some speed, but oftentimes when we think of equilibrium, we often think of things with a zero velocity, okay? This spring just sitting here like this. And we call this its equilibrium point. So as it turns out, when we deform a spring away from its equilibrium point, the force that it produces, so force of the spring, is proportional to how much we deform it. So we have some factor here, and then we have the distance that we deform it. And the force that the spring applies is proportional to the distance that we have deformed it. This is called Hooke's law, okay? This is Hooke's law. And it says the force of a spring is going to be proportional to the distance that you deformed it, and in the opposite direction. Notice we have the negative sign. This K K is the spring constant. And the spring constant is a property of the spring, okay? It depends on what the spring's made out of, how tightly the coils are wound, maybe how thick the metal is, things like that, okay? The spring constant is always going to be a property of the individual spring. And if we look at the equation, if we look at Hooke's law, we know that this is going to have units of newtons, and this is going to have units of meters, okay, with some prefix, okay, so maybe it's going to be centimeters or millimeters or whatever, but it's going to have units of length. So this guy, for this right side to return a force, well, this must have units of newtons per meter, okay? And so this spring constant tells you kind of the strength of the spring in terms of how many newtons is it going to apply per meter of compression, okay? This might be given in newtons per centimeter or newtons per millimeter, but it's always going to tell you how much force the spring applies per unit of compression or extension, okay? How much per unit of displacement from equilibrium. So if we look at Hooke's law and we give ourselves a coordinate system, let's say to the right is x hat, you can see that if we take this spring and we stretch it some distance x, then Hooke's law tells us that the force that it pulls back will be minus k x, okay? So we've displaced it to the right here, some distance x, and then Hooke's law tells us that the force will be back this way, okay? Just like we know a spring acts. So the equation represents the real world, so it acts as we expect it to, right? We displace the spring outward, and so it pulls back in the negative direction, okay? It pulls back toward equilibrium. On the other hand, with this same coordinate system in place, if I compress the spring by some distance x, okay, when I do that, my displacement is negative, right? I'm displacing it in the negative direction. So I have minus k, and then x is minus x because I'm displacing it in the negative direction, and so the force will end up being kx, right? So when I displace it in the negative direction, Hooke's law tells me that the spring will push back in the positive direction, okay? Fs here. So Hooke's law contains this information that I was talking about the way springs act when they're displaced from equilibrium. And we can use this to find the magnitude of the force that they will apply in their attempt to get back to equilibrium, okay? So in a car suspension, when I go over a big bump, the spring pushes harder, right? When I go over a big bump that displaces by a greater displacement, the spring pushes harder as it tries to get back to equilibrium, okay? And this equation is true at every moment in time. So when I go over a big bump, when the spring is displaced to here, it pushes harder than when it's displaced to here, okay? And as it goes back to equilibrium, it pushes with less and less force, okay, as it moves. So because this equation is dependent upon the displacement, as the displacement changes, the force that the spring applies changes. So when I push a spring way down here, it pushes really hard, but then as I let it go, it doesn't keep pushing with some kind of memory of the fact that I displaced it by this much. It only pushes as hard as the current displacement. So as I release it back to the top, it only pushes as hard as the current displacement up to the point that when it reaches equilibrium again, it now exerts no force. So we'll talk about springs more in the future of this class. We're going to talk about them more, especially when we start to talk about energy. And we'll get into a little bit more detail about springs at that point. But I just wanted to introduce springs as a concept to you guys here. And I want you guys to know Hooke's law up here. So I'd like you to know, for now, Hooke's law that the force that a spring applies when I displace it from equilibrium is always going to be proportional to the distance that I displace it from equilibrium, and it's going to be that distance times this factor, this spring constant, and that this spring constant is a property of the spring. So now let's move on to a couple of example problems that I wanted to solve today. So let's look at this first one. Consider a 1.1 kilogram block on a 32-degree ramp with a coefficient of static friction of 0.51 and a coefficient of kinetic friction of 0.44. The block is connected to a string that runs up the ramp and over a pulley at the top of the ramp. Hanging from the other end of the string is a 1.1 kilogram block. Will the blocks move? If they do, which direction will they move, and what will the acceleration be? So let's set up this problem first. This problem, we have our classic block on a ramp, okay, with the force of gravity pointing down. We have the normal force pointing up. And then we have it attached to a string here that attaches it to this other block down here, okay? And we'll call this guy M1, and we'll call this guy M2. And along this string, oh, that should connect to our little center of mass here. Along this string, we're going to have tension, okay? And same thing for this one. Along this string, we're going to have tension. And then this one is going to have the force of gravity pulling down. Okay? And then, for now, let's just put the force of friction in like this. Notice that the two blocks have the same mass this time. So, in this case, you guys may not be sure which way this is going to move, right? We're not sure if this is going to move this way or if it's going to move this way, okay? You might be able to make a guess, but you can imagine that even if you could guess this one, there may be some combination of masses that you might not be able to guess. So I wanted to solve a problem where we're not sure which way it's going to move, okay? Or at least we say we're not sure which way it's going to move. And then I want to show you guys how to figure out what happens, okay? So we have this system, and we have forces drawn on it. And what I want to do is set up a coordinate system here. And I'm going to set up this one that we like to use for blocks on ramps, okay, because it's very convenient. And what I want to show you guys is that with the tension on this rope and this pulley, I can think about my coordinate system as going along the ramp and wrapping around the pulley like this, okay? Now that's a funky coordinate system. It wouldn't define everything in space the same way, but I want you to just think about it that way for a second. And then I'm going to set up x hat for this other block to be down, okay? Now the reason that I'm doing this, the reason that I'm thinking about this way, is because if I'm not sure which way the blocks will go, I can let the math tell me, but I have to make sure that the directions match. So if I solve it for A, and I'm going to say, okay, if A is positive, we're going this way, I have to make sure that that's true of this one too. Because remember, when they're attached by this rope, and we're going to assume that it doesn't stretch or anything like that, then their accelerations have to be the same, right? If this rope can't stretch or anything and I pull this one down a little bit, then this one has to move a little bit, right? And you can see that they'll move together where this one goes to the right and this one goes down. Or if I was to pull on this block a little bit and move it a little bit to the left, this one would have to go up a little bit, okay? So they have to move together like that when they're connected by this rope that doesn't stretch. But I have to pick coordinate systems so that when A is positive here, it's also true that A is positive here. And I wanted to show you that in this example explicitly because I think I showed you an example where I knew which way the system was going to move. And so I had different signs on A for the different blocks. And that's fine as long as you keep track of your signs and you track them all the way through the problem. But in this case, I want A to have the same sign for the same direction of motion of the whole system, because I'm going to use the math to tell me which way it moves. Okay? So now with this system set up, we can say mass 1 is 1.1 kilograms, and that's equal to mass 2, right? They're both 1.1 kilograms. Theta equals 32 degrees. And mu sub k is 0.44. And mu sub s is 0.51. Okay? Now remember, in this coordinate system for this top block up here, this coordinate system here puts all of our forces along the coordinate system except gravity. So we'll have to break gravity into components, and it's going to be Fgx and Fgy. And remember when we talked about mass versus weight, okay, a couple of lectures ago, we said that mass was a measure of how much stuff there was, and weight was a measure of the force of gravity acting on you, right? This is the force of gravity. And remember, we said your weight, the force of gravity, equals mg, right? So every time we have the force of gravity in a problem, it's going to be mg. For this block, for block 1, it's m1g. For this block over here, it's going to be m2g, right? But it'll always be the mass of the object times the acceleration that gravity would provide in free fall. And then what the problem wants us to do is figure out, 1, are the blocks going to move? And 2, if they do move, which direction will they move, and what will the acceleration be? So we're going to draw it like this first, and we're going to solve. We're actually going to do the last part first, okay? If they do move, which direction will they move? Okay, so let's look at this problem. We know we're going to solve this with Newton's second law. The sum of the forces is equal to mass times acceleration. Okay? So let's first look at, put my coordinate system in here. Let's first look at the y direction for the block 1, okay? Remember M1 up here, M2 down here. So the y direction for M1, we have the normal force pointing up, okay? And then we have the y component of gravity pointing down, Fgy. And then we're not going to have any acceleration in that because the block doesn't fly up off the ramp and it doesn't fall down through the ramp, okay? And so that tells us that the normal force minus mg, and then the y component is cos theta. Remember, if we break this down into components, this angle right here is still theta. And that equals 0. And so therefore, the normal force equals mg cos theta. Okay. So the y direction allowed us to solve for the normal force. Now, let's look at the x direction of block 1. So in the positive x, we have tension. And then in the negative x, we have the force of gravity in the x component. And then also the way I've drawn it up here, we have minus F. And we're going to look at if it's moving. So we're going to look at Fk. And then that's equal to M1A. And then for block 2, we'll look at, I called it the x-hat, but the vertical direction here. And for block 2, we have, in this case, Fg2 in the positive direction minus tension, okay? And we'll say that equals M2A. And right now, A is positive, but the truth is we're being non-committal, okay? We're going to see if A is positive or negative when we get the answer, okay? And so then that tells us that tension, well, hold on. Let me take a little bit smaller steps here, okay? So Fg2 is going to be m2g, the weight of block 2, and then that's minus T equals mass 2 times acceleration. And that tells us that tension is going to equal m2 times g minus A, okay? So now we apply Newton's third law. And remember, tension right now is an interaction between block 1 and block 2, right? It's these two blocks pulling on each other. And so tension, as we see in the picture here, it has two directions. It's going this way to pull on block 2, and it's going this way to go back and pull on block 1, okay? So block 1 pulling on block 2 is this way. Block 2 pulling on block 1 is this way. So this interaction has two sides, just like they always do. And because it's a single interaction between block 1 and block 2, it has just one magnitude, which means that this T from block 1 and this T from block 2, well, they're the same, okay? They have the same magnitude. So this tension from block 2 can be plugged in over here in the equation for block 1. So if we do that, we put in m2 g minus A minus the force of gravity in the x direction, which is m1. Remember, this was for block 1. m1g, and then sine theta is the x direction in this case, minus the force of kinetic friction equals m1a. So now remember that this force of kinetic friction, Fk, is always equal to mu k times the normal force, okay? And we solved for the normal force in the very first thing we did in this problem. So this is equal to mu sub k m1 g cos theta. And we can plug that into our equation as well. So m2 times g minus A minus m1g sine theta minus mu sub k m1g cos theta equals m1a. So now if we look at this, we see that we have A in here just twice, and we can solve for A, okay? For all the rest of the stuff in here, m2g, m1, theta, mu k, we know all of that stuff. So all we have to do here is solve for A now. So let's get all the A's on the same side of the equation first. So we have m1a, and then we have the m2a here, so plus m2a. And that equals m2g minus m1 g sine theta minus mu sub k m1 g cos theta. And then that means that A equals g times m2 minus m1 sine theta minus mu sub k m1 cos theta. And all of that is over from this left side here, m1 plus m2. And then the question is, did we choose correctly? Okay, so we picked friction down the ramp, and the question is that correct? So if our A ended up negative, we would want to switch and solve it for friction pointing up the ramp, right? Because if it turned out negative, what I'm saying is remember, this is the force of gravity on block 1, and this is the force of friction, and I'm saying that they add up to more than the force of gravity on M2 here, right? This is the force of gravity on M2, and that's pulling on block 1. So if these added up to more than M2 here, this M1 sine theta and mu sub k M1 cos theta, then I would get a negative answer, and it would tell me, that negative on my answer would tell me that I chose the wrong direction, right? It would tell me that what it looks like is the block is probably going to slide down the ramp, but I need to solve it for the other way, because right now I have friction going in the same direction as the motion, if it turns out to be negative. If it turns out to be positive, then it tells me that I've chosen correctly, okay? Because I have A going in the positive x, which up in our picture is this direction, right? And I have friction going in this other direction, the negative direction, and that's correct, okay? So if A turns out positive and I have a negative friction over here, then that's the correct way for those things to end up, right? They should always have opposite signs. If A turned out negative and friction was part of the thing that was speeding up A, we would know that's a problem, right? Friction only slows things down. It doesn't speed things up. So the question is, does this turn out to be positive? So you could plug in the numbers. That's one way to check it. I can plug in the masses and the angles and everything and see what is the number. Is it positive or negative? But another thing I can do is look at this and figure out whether I think it's going to be negative by inspection. So I know that M2 equals M1. And sine theta, I know, is going to be less than 1, right? In fact, because my angle is less than 45 degrees, I know that sine theta is less than cosine theta, okay? For less than 45 degrees, sine theta is less than cosine theta. As we go above 45 degrees, sine theta is bigger than cosine theta. But I also have this little guy right here that I know is much less than 1, okay? It's 0.44. So I have a number that's M1 times a number that's much less than 1, and M1 times two numbers that are much less than 1. So I expect that this will probably be positive. So let's put in the numbers, and let's see if that expectation is correct. So if I put in the numbers just for this top piece, what I'll get is G over M1 plus M2. And masses are always positive, so that denominator is always going to be positive. What I end up with is 0.11. So what I end up with is going to be a positive number overall. So I chose the correct direction when I did this. So this tells us that if they do move, the blocks will move this way. Block 1 will go up the ramp. Block 2 will drop down. Okay? They'll move around in this way, the positive direction in my two coordinate systems. And this will be the acceleration if they do move. Okay? So what do the units on this look like? Units, I have meters per second squared, and then that's multiplied by kilograms on the top and kilograms on the bottom. So I end up with meters per second squared, which is the appropriate units, okay? And then sanity, you see I have M2 minus something times M1 minus something times M1, okay? So this thing is always going to be less than if I had M2 plus M1, right? So what I end up with is that A is less than G. And that makes sense, right? No matter what I do, if we just think even about block 2 for a second, think about block 2 sitting here. If it was in free fall, right, then the acceleration would be little g. So no matter what block 1 is, no matter how little it weighs, I'm adding a tension to it in the other direction. So I have to have an acceleration that's smaller than g. No matter how small block 1 is, no matter how much less it is than little g, I must have an acceleration that's smaller than little g if I'm going to connect these two blocks in this way. Okay? And with them being the same mass and there being friction on block 1, okay, what turns out is I actually have a much less than g. Okay, we're going to have a little tiny a. But no matter what happens, if I connect the two blocks in this way, if we just think about block 2, we should know immediately it must have a smaller acceleration than the little g, because that tension is going to slow it down from free fall. So that makes sense, okay? Now, I think that's the only sanity check that we want to do right now. The masses are showing up in a lot of places, so I wouldn't ask you guys to necessarily check the masses on this. We are kind of checking the masses by just saying that A is less than G, because that's the reason that A is less than G is what happens with this fraction, right? The only other thing that we might look at is, see, mu K only shows up once in here. And we see that as mu K gets bigger, A gets smaller. Right? That's the way it's in the equation. It's a minus over here. So the bigger I make it, the smaller I make A. And that makes sense, right? If I apply more and more friction to block 1, I just slow the system down more and more. So that makes sense. So our units look good. Our sanity looks good. So if the blocks do move, what kind of an acceleration are we going to have? What magnitude are we going to have here? So if we plug in the numbers, we find that A is going to equal 0.48 meters per second squared. Okay, so the first thing we said is, let's assume the blocks are moving, and if they do move, they're going to move like this, okay? We're going to have this expression for A, and it turns out that it's 0.48 meters per second squared. Okay? But now, let's go back and let's answer the first question that was in this problem. Will the blocks move? So, will the blocks move is a question about the static friction, right? And in the y direction for the first block, nothing changed, right? In that case, there was no acceleration in the y direction anyway, and what it ended up telling us was what the normal force is on block 1. Okay? Now for block 1, we know that if they move, they're going to move this way, right? They're going to move block 1 up the ramp, block 2 descending. So now let's look at static friction. So we'll make this a little F sub S. And consider that. So we still would have tension pulling up the ramp, right? And we still would have mg sine theta, the force of gravity pulling down the ramp. And we still would have static friction pulling down, okay? Because we know if they did move, block 1 would go up the ramp. So the net forces on block 1, well, they must be up the ramp, right? The net forces outside of friction, they must be up the ramp if block 1 would move up the ramp independent, or if it did move, okay? So we know we have the right direction on static friction here. And that's equal to ma. But in this case, it's not going to move, right? If we're solving for static friction now, it can't be moving in static friction by definition. It can't be sliding along this ramp. So this A must be 0, okay? And then if we do the same thing for block 2, we would have the force of gravity on block 2, m2g, pulling down, right? That's the positive direction in this coordinate system. And then minus tension pulling up. And again, that's equal to M2 times A, but A is 0, right? They're connected by this string. So if block 1 can't move, well then block 2 can't either. And this is 0. And this tells us that in this case, tension is equal to M2G. Okay? Notice this is larger than before. Larger was M2G minus M2A, right? Minus the acceleration. So the fact that we're not letting it move now means that tension has to support the entire weight of block 2. If I'm letting block 2 fall, I'm not supporting the entire weight, right? Because there's a net force on it down. So I'm supporting some fraction of the weight of block 2 when it's falling. In this case, where it's sitting still, tension has to support the entire weight of block 2. So the force of tension ends up just being equivalent to the weight of block 2. So we put that in over here. Oh, I should have had an M1 on here, huh? Minus M1 G sine theta minus Fs equals 0. So this, if it was in a static state, this would be the equation. And if we just move Fs to the other side, if it's in a static state, this is the magnitude that the force of static friction must have, okay? It has to support the weight of block 2, right? Because that's the reason that they're not falling, is it's supporting block 2 entirely, minus gravity pulling down on block 1, because it's going to point in the same direction as the static friction, okay? So the portion of gravity that points down the ramp is kind of helping friction. We can think of it that way. That's what our equation's telling us, right? It's block 2 minus, right? So I get to subtract some of the weight of block 2, and the amount I get to subtract is this portion of gravity that points along the ramp on block 1, okay? So it's going to help static friction a little bit. And then the question is this force, this magnitude of force, is it bigger than what static friction can provide? So then the question is, if we replace Fs with mu Sn, and that equals mu S M1G cos theta, then we have mu sub S M1G cos theta equals M2G minus M1G sine theta. And notice that G is everywhere here, so we can cancel G's. And we have mu sub S M1 equals M2 minus M1. Okay? Now, this would be the case, equals would be the case that they exactly match the maximum that static friction could provide. So what we really want to say is that this side, oh, I forgot my trig functions. Goodness gracious. Okay. Let's write it correctly, and then we'll talk about what I was going to talk about here. Cos theta equals M2 minus M1 sine theta. Okay, so what we really want to say is the equals would be if this force on this side was exactly equal to the force that static friction can provide. But it doesn't have to be exactly equal, right? We know static friction could provide up to this much force, but it doesn't have to. It will only provide the amount that it absolutely needs to. It will only do what's strictly required of it. So what we really want to say is that this side on the left is greater than or equal to the side on the right, okay? So if that's true, if the thing on the left is greater than or equal to the thing on the right, then we will end up with a block that does not move, okay? Because static friction can provide this much force at a maximum. So if this is greater than or equal to this piece, this whole right side, then static friction can provide enough force for the blocks to not move, okay? So the question is this equation right here true? And for this one, I think I'm just going to recommend that you guys just plug in the numbers and see if it's true, okay? So let's go ahead and do it. Let's do it that way here as well. So if I plug in the numbers, what I get on the left side is a 0.475 kilograms. And then I have my greater or equal to. And then on the right side, what I got for the right side was 0.517 kilograms. Okay? So by plugging in the numbers in this thing, and in this case, I left it M1 and M2. You can see that we could have simplified the math by canceling the masses because they're equivalent up here. But I want this example to be general, and they wouldn't necessarily, in a question like this, they don't have to be equal, right? They wouldn't have to be equal. So in this case, we see that we're saying 0.475 is greater than or equal to 0.517. This is a false statement, right? This one doesn't check out. So the fact that this is false means the blocks do move, okay? And when they move like this up here that we already solved, okay? So the blocks move, and when they move with an acceleration that we've already solved for. It's a little tiny acceleration, but they are going to move. Okay, so let's finish our lecture today with just one more example problem. For this example, we have a plastic block sliding down a metal ramp. We know that the ramp is a 43-degree ramp. If we see that the block is sliding down the ramp at a constant velocity, what is the coefficient of kinetic friction? So we have some block sliding down a ramp. So let's draw that. We have our ramp, we have our block, and it's sliding down the ramp. Okay, so it has some V here. We have theta, and we know we have kinetic friction going back up as it slides down the ramp. So normal to the ramp is the normal force, and pulling straight down, as always, is the force of gravity. And remember, we break it into components. The y component over here, and the x component here. And this angle in here is theta. Okay, so we have that. Nice and simple. And the only thing they really told us is that theta equals 43 degrees. Okay? And then they want to know mu sub k equals what? Okay, so we know we're going to solve this one with Newton's second law. We're dealing with a bunch of forces here, right? So the sum of the forces is equal to mass times acceleration. And let's put our coordinate system in. I'm going to point x down the ramp this time. I wish I had drawn this picture the other way. It gives me the heebie-jeebies a little bit to point x left and y up like this, because usually you want z to point out of the page, not into the page, and z is always x cross y. So in this case, I have z pointing into the page, or if I put z pointing out of the page, I have a left-handed coordinate system, both of which are perfectly fine. There's nothing wrong with them, but they give me the heebie-jeebies a little bit. So for physics majors someday, it will probably also make you a little uncomfortable to see left-handed coordinate systems. But whatever. We're going to point x down the ramp because I want to, and we're going to point y up because we always do. Okay? So remember, we have our components. And now let's solve the y first. The y is generally easier in these block sliding down a ramp problems. We have n in the up in the y coordinate, and we have f g sub y pointing down, and that equals 0. The block doesn't fly up off the ramp or fall down through it. And then that tells us that n equals mg cos theta, right? The weight, and then cos because the y component here is next to the angle theta. And then let's look at the x direction. So in the x direction, remember now I have down as the positive direction. So we have f gx pointing down, and then minus the force of kinetic friction pointing up equals ma. But now remember, zero acceleration doesn't mean zero velocity. It means a constant velocity. A constant velocity of 0 is a common constant velocity, but all constant velocities have a 0 acceleration. Okay? So this a in this problem is 0. And that makes this problem just like solving a static friction problem. Okay? But we have a kinetic coefficient of friction. And that is really the key insight to this problem. At that point, then I'm just writing mg sine theta, that's the x component of the object's weight, minus mu sub k times the normal force, and that equals mg sine theta minus mu sub k, and then the normal force is mg cos theta, and that equals 0. Okay? And then this piece, what I want to solve for is mu sub k. So I'm going to take this term to the other side and write mu sub k mg cos theta equals mg sine theta. The m's cancel, the g's cancel, and what I end up with is mu sub k equals sine theta over cosine theta equals the tangent of theta. So I end up with this really simple answer. So let's check our answer because we like to be thorough. The units, we have a coefficient of kinetic friction which has no units. And that's equal to tangent of some angle which has no units. So the units work out just fine. Sanity, well, mu sub k goes up as theta goes up from 0 to 90 degrees. Okay? Now, tangent just increases as theta increases from 0 to 9 degrees. Okay? So, if I am sliding with constant velocity on a steeper and steeper ramp as theta goes up, then I must have a bigger coefficient of friction because more of my gravitational force points down the ramp, right? So the steeper I make the ramp, if I have a ramp like this, you can see when I draw gravity straight down, the x component points closer to this angle, right? Or, well, the x component is always going to point in that angle. That's how we set it up. But you can see gravity, more of the x component is along this than if I set it up like this. Then when my gravity pulls straight down and I have my coordinate system like this, I have more of the gravitational component in the y component, okay? So the less steep my ramp is, the more gravity pulls the block into the ramp. And as I make it steeper and steeper, the less gravity pulls the block into the ramp and the more it pulls it down the ramp. Okay? So this relationship where mu sub k must be bigger if theta is bigger makes sense because to slide with a constant velocity, my force of friction, which is dependent on this mu sub k, is always going to be need to balance out the force of gravity in the x direction. Okay? So that one makes sense. Obviously, there's nothing else to sanity check here because, as it turns out, the reason that the problem only gives the angle here is because if a block is sliding down a ramp with constant velocity, all we need to know is the angle of the ramp to figure out the coefficient of kinetic friction between the two objects. Okay? And this one, tangent of 43 degrees is equal to 0.93. So this coefficient of friction must be 0.93. So there's a couple more examples of force problems. Remember that we covered springs. We learned about Hooke's law today. And we'll do more of this in the future. We'll have more force problems as we go forward in the class. And we'll bring springs back up again, probably when we talk about energy. But you may have some homework problems from time to time where there's a spring applying a force, and you'll just need to know that the force that a spring applies is the magnitude of that force is found with Hooke's law.